Welcome. In this video, we will explore vectors in three-dimensional space, a fundamental concept in IB mathematics analysis and approaches higher level. By the end of this session, you will be able to represent vectors in 3D, calculate their magnitude, perform basic vector operations, and apply key algebraic properties to solve problems. We'll begin by extending our understanding of vectors from 2 dimensions to 3. In 2 dimensions, we use the x and y axes. In 3 dimensions, we add a third axis, the z-axis, which is mutually perpendicular to both the x and y axes. This creates a 3D Cartesian coordinate system. A point P in this space is defined by 3 coordinates, x, y, and z. We write this as P of x, y, z. The position vector of this point P, denoted as OP, is a vector that starts at the origin O and ends at point P. We can express this vector in 2 main forms, component form and unit vector form. In component form, we write the vector as a column matrix containing the coordinates of the point P. So the vector OP is the column vector x, y, z. In unit vector form, we use the base unit vectors I, j, and k. The vector I is 1, 0, 0, and points along the x-axis. The vector j is 0, 1, 0, and points along the y-axis. The vector k is 0, 0, 1, and points along the z-axis. So the position vector OP can be written as x times I plus y times j plus z times k. Both forms represent the same vector. Now, let's discuss the magnitude of a vector. The magnitude is simply the length of the vector. For a vector A, with components a1, a 2, and a 3, its magnitude, written as the magnitude of A, is found using a 3D extension of the Pythagorean theorem. Let's see why this is the case. Consider the position vector OP for a point P with coordinates A, B, C. We can visualize this as the diagonal of a cuboid with sides of length A, B, and C. First, let's find the length of the diagonal on the xy plane, which connects the origin to the point A, B, 0. Let's call this length OB. Using the standard Pythagorean theorem in 2D, OB squared equals A squared plus B squared. Now, consider the right-angled triangle formed by the origin O, the point A, B, 0, and the point P with coordinates A, B, C. The hypotenuse of this triangle is the vector OP. The other 2 sides are the diagonal OB and the vertical line segment BP, which has length C. Applying the Pythagorean theorem again, OP squared equals OB squared plus BP squared. Substituting our expression for OB squared, we get that OP squared is A squared plus B squared plus C squared. Taking the square root gives us the magnitude of the vector OP, which is the square root of A squared plus B squared plus C squared. This formula is crucial for many vector calculations. Let's work through an example to solidify this concept. We'll find the magnitude of a vector given in unit vector form. Suppose we have the vector A equals 2i plus j plus 4k. Our goal is to find its length, n, or magnitude. First, it's often helpful to convert the vector to component form. The coefficients of I, j, and k become the components of the vector. So A is the column vector, 2, 1, 4. Now we can apply the magnitude formula. The magnitude of A is the square root of the sum of the squares of its components. That's the square root of 2 squared plus 1 squared plus 4 squared. Calculating the squares, we get 4 plus 1 plus 16, which sums to 21. Therefore, the magnitude of vector A is the square root of 21 units. This process is the same whether the vector is given in unit vector form or component form. You just need to identify the components correctly. A special type of vector is a unit vector. A unit vector is any vector that has a magnitude of exactly 1. The base vectors I, j, and k are all unit vectors. For example, the magnitude of I is the square root of 1 squared plus 0 squared plus 0 squared, which is 1. Let's determine if a given vector is a unit vector. Consider the vector C equals negative 2/3, 1/3, 2/3. To check if it's a unit vector, we must calculate its magnitude. The magnitude of C is the square root of the sum of the squares of its components. That's the square root of negative 2/3 squared plus 1/3 squared plus 2/3 squared. Squaring the fractions, we get 4/9 plus 1/9 plus 4/9. Adding these together gives us 9/9, which simplifies to 1. The square root of 1 is 1. Since the magnitude of c is 1, we can confirm that c is indeed a unit vector. Now, let's look at how to find an unknown component of a vector when its magnitude is known. Suppose we have a vector A with components -2, m, and 1. We are told that its length is the square root of 14 units. We need to find the possible values of m. We'll start by writing down the magnitude formula for vector A. The magnitude of A is the square root of -2 squared plus m squared plus 1 squared. We are given that this magnitude is equal to the square root of 14. So, we can set up the equation. The square root of 4 plus m squared plus 1 equals the square root of 14. To solve for m, we can square both sides of the equation. This removes the square roots, leaving us with 5 plus m squared equals 14. Subtracting 5 from both sides gives m squared equals 9. Finally, taking the square root of both sides, we find that m can be either 3 or -3. Both of these values would result in a vector with a magnitude of the square root of 14. Now let's move on to operations with vectors in space. The rules for adding, subtracting, and multiplying vectors by scalars are a direct extension of what you've learned in 2 dimensions. Let's define 2 general 3D vectors, A and B, in component form. To add 2 vectors, you simply add their corresponding components. So A plus B is the vector, A1 plus B1, A2 plus B2, A3 plus B3. Similarly, to subtract vectors, you subtract their corresponding components. A minus B is the vector, A1 minus B1, A2 minus B2, A3 minus B3. To multiply a vector by a scalar k, you multiply each component of the vector by that scalar. K times A is the vector, K times a 1, K times a 2, K times a 3. These rules are straightforward and apply to any number of dimensions. Let's apply these rules with a worked example. Given the vectors A equals -1, 3, 2, and B equals 3, 0, -1, we will find A plus B, 2A minus B, and the magnitude of A times B. First, let's find A plus B. We add the corresponding components, -1 plus 3, 3 plus 0, and 2 plus -1. This gives us the vector 2, 3, 1. Next, let's find 2A minus B. First, we perform the scalar multiplication. 2 times A is 2 times -1, 2 times 3, and 2 times 2, which is -2, 6, 4. Then we subtract vector B component by component. This gives us the vector -5, 6, 5. Finally, let's find the magnitude of A times B. First, we need to calculate the magnitude of A. This is the square root of -1 squared plus 3 squared plus 2 squared, which is the square root of 14. Now we multiply this scalar, the square root of 14, by vector B. We multiply each component of B by the square root of 14. The result is the vector, 3 times the square root of 14, 0, negative the square root of 14. Vector algebra follows many of the same rules as real number algebra. Understanding these properties is key to solving more complex vector equations. Here are some of the most important properties. Vector addition is commutative, meaning A plus B equals B plus A. It's also associative, so the order of addition doesn't matter. The zero vector, 0, acts as an additive identity. Every vector A has an additive inverse, -A, such that their sum is the zero vector. Scalar multiplication is distributive over vector addition. And a very important property is that the magnitude of a scalar k times a vector A is the absolute value of k times the magnitude of A. This means that multiplying a vector by a scalar k scales its length by a factor of the absolute value of k. A crucial point to remember is that there is no such thing as dividing a vector by a scalar. Instead, we multiply by the reciprocal scalar. For example, if you have the equation 2x equals a, you don't write x equals a over 2. You write x equals 1/2 times a. The expression a over 2 has no meaning in vector algebra. Let's use these properties to solve a vector equation for an unknown vector x. Suppose we have the equation x plus a equals b. Our goal is to isolate x. We can treat this much like a regular algebraic equation. To get x by itself, we need to eliminate the vector a from the left side. We can do this by adding the additive inverse of a, which is negative a, to both sides of the equation. On the left side, a plus negative a equals the 0 vector. On the right side, b plus negative a is the same as b minus a. Since adding the 0 vector doesn't change x, we are left with our solution, x equals b minus a. This shows how the properties of vector algebra allow us to manipulate vector equations. Let's tackle a more complex problem that combines several concepts we've learned. We are given two vectors, a and b, and we know their magnitudes. The magnitude of a is 5 units, and the magnitude of b is 3 units. We need to find the range of possible values for the magnitude of the vector c, which is a plus b. This problem is best understood geometrically. Imagine two vectors, a and b, starting from the same point. The vector c, which is their sum, forms the third side of a triangle. This is known as the triangle law of vector addition. The key to solving this is the triangle inequality theorem, which states that the length of any side of a triangle must be less than or equal to the sum of the lengths of the other two sides. In our case, this means the magnitude of c must be less than or equal to the magnitude of a plus the magnitude of b. Substituting the given magnitudes, we find that the magnitude of c must be less than or equal to 5 plus 3, which is 8. This gives us our upper bound. Now for the lower bound. The smallest possible magnitude for c occurs when the vectors a and b point in opposite directions. In this case, the magnitude of their sum is the absolute value of the difference of their magnitudes. This is the absolute value of 5 minus 3, which is 2. Combining the upper and lower bounds, we find that the magnitude of c must be between 2 and 8, inclusive. This is the range of possible values for the magnitude of the sum of the two vectors. Let's recap what we've covered. We started by defining vectors in 3D space using both component and unit vector forms. We then learned how to calculate the magnitude of a 3D vector using the Pythagorean theorem. We explored the concept of unit vectors and how to find unknown components given a magnitude. Finally, we reviewed the rules for vector addition, subtraction, and scalar multiplication, and we saw how the properties of vector algebra allow us to solve vector equations. You are now equipped to handle these fundamental vector operations in 3 dimensions. To help you master these concepts, here are 5 practice questions in the style of IB assessment. Pause the video, work through them, and then check your solutions. Question 1. Given vectors a and b, find the magnitude of 2a minus b. Question 2. Find the value of k for a unit vector. Question 3. Find the possible values of m for a vector with a given length. Question 4. Solve a vector equation for an unknown vector x. And question 5. Find the range of possible values for the magnitude of the sum of two vectors. Here are the fully worked solutions. Compare them to your own. For question 1, we first calculate 2a minus b, which is the vector 4 minus 5, 6. Its magnitude is the square root of 77. For question 2, we set the magnitude of v to 1. This leads to the equation k squared plus 5 ninths equals 1, so k squared is 4 ninths, and k is plus or minus 2/3. For question 3, we set the magnitude of u to 6. This gives us 25 plus m squared equals 36, so m squared is 11, and m is plus or minus the square root of 11. For question 4, we first rearrange the equation to solve for x. We get x equals 1/3 of the vector 0, minus 1, 5. And for question 5, using the triangle inequality, the magnitude of p plus q is between the absolute difference of their magnitudes, which is 3, and the sum of their magnitudes, which is 11. Thank you for watching. Keep practicing these concepts to build a strong foundation for your IB studies. In this final scene, we'll quickly revisit the 2D vector example from your notes to ensure you can apply these same principles to two-dimensional vectors. We are given two 2D vectors, r and s, in unit vector form. We need to find the magnitude of the vector p, which is r minus 2's. The process is identical to what we did in 3D. First, we'll find the vector p. We substitute the expressions for r and s. This gives us 2i plus 3j minus 2 times the quantity negative I plus 4j. Distributing the negative 2, we get 2i plus 3j plus 2i minus 8j. Combining the I components and the j components, we find that the vector p is 4i minus 5j. Now that we have the vector p, we can find its magnitude. The magnitude of p is the square root of 4 squared plus negative 5 squared. This is the square root of 16 plus 25, which is the square root of 41 units. As you can see, the principles of vector algebra and magnitude calculation apply seamlessly to both 2 and 3 dimensions. This concludes our session on vectors in space.